Yeah, let's start. So we are looking at bin packing problem. Yeah. So this was the problem we were looking at, is that you are given n items with sizes between 0 and 1, and we want to pack these items or just fill these items into unit size bins. Okay. Each bin is of size 1, and we want to fill these items into these bins. And our objective is that the total number of bins used is as minimum as possible. Okay, has plenty of applications, and we had this. So you had many ideas yesterday. So let's assume that these are the objects you want to pack. One is of size 0.3, 0.2, 0.4, 0.5. And you can easily find one packing which uses 3 bins. These are the objects which are allocated. In the first bin, we put these 4 objects. 3 are of 0.2 size, 1 is of 0.2. So the total sum is 0.9, which is less than 1. Similarly, here the total sum is 0.6, which is again less than 1, and here 0.5, which is again less than 1. So you can certainly pack these using 3 bins. The question here is that necessary? Do we really have to use 3 bins? Okay. So what is the minimum number of bins we can have? So we discussed many ideas in the last class, and we'll just continue that. So one idea was that we sum up the weights of all of these. Okay. So here it's 0.3, 0.5, 0.7, 0.9, 1.1, 1.5, and 2. Whatever is the total weight, rounded off to the next integer, that many number of bins we will definitely require. Okay. But every time computing the sum will not tell you the total number of bins. Okay. Because what will happen is the total sum might be 2 or 3, but you can't always split it into 2 bins of size 1 or 3 bins of size 1. Okay. So the total sum might be 2, but there may not exist any subset with total size 1. It might be just crossing 1, and such things might happen. So in that case, you might need larger number of bins. Okay. So one idea was that we try to find such a subset whose total sum is 1. Okay. And then just put it in the individual bin. So in this case, we can indeed find such a subset, but in general case, it may not always be possible. Okay. For instance, we could find this subset 0.5, 0.2, 0.3, and the remaining items, they will go in the other bin. But notice that finding such a subset is a very difficult task. Like you may not always find such a subset because potentially you may have to check for all possible subsets of these given n items, right? And there can be 2 raised to n many such subsets. Can be exponential time algorithm. And in fact, then some of you told that we can look at it as a 0-1 knapsack problem. Okay? That was again a good idea. So what is the knapsack problem? In that case, you just have one bin or bag. Okay? And you are also given the weights of these things and the values of these things. And there you want to minimize the weight but maximize the total value of those objects. This is a different problem in that you have multiple such bags instead of just one bag, and there is no issue of any value of maximizing some value. We just want to pack all these items or fill these bins with these items so that so that all these items get filled. Okay. So you can assume that each of these has value 1. So we are looking at value 10. So there are different things here which make this problem difficult here. And in fact, it is NP complete. And you can give a reduction from this problem to knapsack or knapsack to this problem. Okay. So right. Now we want to give some approximation algorithm because finding an exact problem, this is an NP complete problem. So finding an exact solution is difficult. So what strategy are we going to use? And in fact, there are 2 versions of this problem. One is when you are given these objects all at once. That is what we have generally considered in this course, is that the entire input is given to you in advance. Okay? The entire input is given here, and then you have to decide which to pick first and put it in the first bin and second bin and so on. Okay? There is another version which is called online bin packing, which is that the entire input is not given to you. Okay, I give you these inputs one by one. These objects are given to you one by one. So first you are given 0.3 and then you have to make a decision which bin to put it in. Okay, so first you are given 0.3, let's say you decide to put it in the first bin. Then 0.2 comes and then you have to decide where to put first bin or second bin and so on. So the input is revealed to you one by one, and based on that, you have to make a decision. And once you have put one object in some bin, you cannot remove it back. Okay, you realize, okay, this was not the good option. Let me remove it and put it in some other bin. So you can't do that. So you have to gradually produce the solution as the input is revealed to you. So we won't discuss online algorithms in much detail here, but it's just a good thing to know. Okay. And ideally, we want, in this class, we are just looking at approximation algorithm. So let's just assume that the entire input is given to you and you have to make a decision which object to put in which bin. Okay. Then there was one more idea which said that, okay, let me put the largest object in the first bin. Okay. And then it said that then we'll put some smaller objects. So I'm going to discuss 3 different greedy algorithms for this problem. But before that, we will discuss what your ideas are. Okay. So for instance, let's say we want to find how to get this kind of things where the number of bins is very small. Okay. Then what strategy will you use in this case? Okay. So how can you put the inputs here? Obviously, we want to argue in the general case of bin packing, but let's look at this simple example. And how are you going to pack? Yeah, tell me. What strategy are we going to use? Okay, we have treat given object as an array and find a subarray with sum of bins capacity. Uh, find the subarray with sum of bins capacity. Okay, that is interesting. So what are you going to do here? So let's say this is my array which contains these items 0.3, 0.2, 0.2, 0.2, 0.2, 0.4, and 0.5. So finally, you don't know how many bins you are actually going to use. So if you just sum up all these elements, then you don't have any guarantee. So in this case, the sum was 2, but you don't know whether 2 bins will suffice because then you have to partition this array of each of some one. And that is a difficult problem. So it may not always give you the desired result. So notice that we are just looking for an approximation algorithm. We don't have any hope to solve this problem exactly. So we are okay if we don't get the minimum number of bins. Even if it is close to the minimum, that's completely fine. Okay, we can start from the largest bin. No, so bins are all of equal size, so there is no largest or smallest bin. While putting the other bin, check whether size limit exceeded or not. If yes, take another bin, else add it to the already existing. Yeah, this is certainly one idea. Yeah, this is a good idea. Can certainly do that. And okay, so what we do is in this case, we just put it here. Okay. For instance, this was the strategy used is that we put 0.3 first in this first bin. Okay. Then we look at 0.2. There is space to put 0.2, so we again put it. Again, there is space for another 0.2. Again, there is space for another 0.2. So we keep doing it until there is space in the first bin. And whenever there is no space, then we move to the next bin. Okay. So there was no space for 0.2 because then it will exceed the capacity of this bin. So we put it in the next. Then we put 0.4. Okay. But then there is no space for 0.5. So we put it in the next. Okay. So yeah, this is what is called the next fit algorithm, which is a very standard way to solve this. And we would also like to see how it compares with the optimum. So we know that the optimum arrangement just uses these 2 bins. Instead, we are getting 3 bins here. And we can't hope to get 1 bin, right? Because then the capacity of each bin is just 1. And because capacity of each bin is 1, but the sum of these weights is much larger than 1. Okay, so we need at least 2 bins. Okay, there is one more idea. You can traverse it in descending order also. Yeah, you can do that. So what do we get in descending order? Okay. Let's see. So if you go in descending order, we put 0.5 in the first thing, then we put another 0.4. There is still space for that. Then what happens? Next highest is 0.3. Okay. So we put 0.3, 0.2, 0.2, 0.2. All of these will come, and another 0.2 in another bit because there is no space for that. Yeah, so it's roughly equivalent whichever way you go. Whether you go in ascending order or the descending order. But we still haven't got these 2 bins, right? Whether you go in ascending order or descending order, you can't get this particular arrangement. So how can we find this arrangement? So what strategy will you use to get this particular? Okay, so these are our initial weights, and we want some strategy to find this. So there is one more idea, which is that uh, top two or three largest elements are not taken together. Yeah, that is a good observation. Uh, but you have to give some algorithm. You can't just base it on this observation, right? So you have to decide once are you going to put. So one thing we can all agree that uh, let's say we put the largest element first. Okay, okay, there is one more idea. Uh, is using some sort the objects, okay, and put the largest object in the bin. Okay, we put 0.5 and find rest of the objects for a bin from starting of object array and put the objects. And we will take a hash map for distance from larger object. Okay, that's an interesting idea. And we will have to put it in first and put according. Okay, so in this case, what are you doing is that you put the largest object. We have sorted all these things. Okay, and we put the largest object first. Okay, so let's say we put 0.5 and find the rest of the objects for a bin from the starting of object array. Okay, so starting has all these 0.2, 0.2, 0.2 elements and put the objects. So what is your hash map doing exactly? So after 0.5, should I put all the 0.2 weights? Like we will put 5 and then distance of 5 minus 2 equal to 3. We can put it in bin and find the object with distance 2. Okay. So you want distance to be smaller, is it? If I understand it correctly. Okay. Yeah, that is a good idea. So what he's saying is that you put the largest object first, 0.5. Okay? And then he's finding the closest thing to 0.5. But here I have 0.4 also. So am I going to put 0.4 next? But then again, we have a problem that in the next bin, so in one bin, I will put 0.5 in the 0.5 and 0.4. In the next bin, I'll put 0.3, 0.2, 0.2. And in the third bin, again, I'll have to put 0. So again, it is a bit, don't understand how it exactly works. What if we consider the maximum distance? Yeah, it is not exactly convincing. But then again, if you take the maximum distance, then you will put 0.5, 0.2. Then there are again elements with 0.2. And but you don't get the optimal one still. Okay, there's one more thing. After filling the first bin with the items, such that the next items exceed the available bin's capacity, we can remove some items. Okay, and check if there is an item not filled that exactly fits the bin and bin is filled fully. Okay, so what you are saying is uh, assuming that you are going in the sorted order. So we put 0.2 first, then another 0.2, 0.2. So all the 4.2s come first. And then the next item exceeds the available bin's capacity. Okay, so 0.3 is now exceeding the bin's capacity. And we can remove that item. Can remove some items. Okay, so 0.3 is not filling it completely. So we'll remove some 0.2. Yeah, but again, it will go back into the first case. How do I get this particular arrangement? That's the main question. Okay, one more idea. Place the next item in the smallest possible spot. That is, put it in the bin so that the smallest empty space is left. Okay, yeah, that is a good idea. He wants the smallest empty space here. Okay. So first we put 0.5 so that the smallest empty space is remaining. Okay. And then what we'll do, you'll put 0.4. But again, it's the problematic, right? Okay. We have one more. So put 5222. Okay. But then we exceeded by 1. So now we will sum from 2 plus 1 equal to 3. Does this exist in the object? Okay. Yes. Then replace. If not, then 2 plus 2 plus 1 equal to 5. Does this exist? Yes. Then put it in the answer. Remove 2 from front and we will do this further. Okay. So, yeah, it's not completely clear, but what you are saying is I'll put some random object and see whether it is exceeded or not. And if not, and if it is exceeding by some value, then we will check whether some uh, object with value equal to the present value plus 1 is there or not. Okay. Yeah, actually, it's very difficult to find this two bins arrangement, right? So, seems all algorithms are currently falling short of getting a two bin arrangement. Okay, so we have one more thing. We can use hashing while putting the elements in the bin. Check whether the empty sized element is present or not. If yes, then add it, else add another bin. Okay, while putting 0.4 and 0.5 containing bin, check hash 1 minus 0.4 plus 0.5. Okay, but what this is doing is it's just checking whether the total size is less than 1 or not. Yeah, so you can see how hard this problem is bin packing because even for which looks simple, but getting this arrangement into two bins turns out to be extremely difficult. Okay. So it is one of those things which will check whether point one is present or not. Uh, while putting point 4 in point 5 containing bin. Okay, now I understand. So if point 1 is not present, then you will put point 4 in another bin. Okay. Then what do you do? But here, again, you might have to check for subsets, right? Because you would have to sum up some elements in the original array and then check whether those can be filled inside. So your algorithm seems to be making use of the fact that there are these three elements. And once I put one element, the decision whether to put another element depends on something can be filled inside or not. Maybe there are four elements here. Then what will you do? Okay, there is one more idea, which is four twos wherein bin, in this case, while applying my algorithm, and four twos wherein bins 1 and 2, okay, can be replaced by 3. Can be replaced by 3. Now the empty space in bin 1 is 1. Okay, let me go back to your original algorithm, which is, okay, so you are removing some things. Now the empty space in bin 1 is 1. Okay, then we can remove another 2. We find that there is no unfilled item which can be packed into the bin 1, and there is an improvement in arrangement. Hence, we remove another 2, and we find that packing 5, the bin 1 is filled fully, and we can move on to the next bin. Okay, let me start from the starting. Let's say I put 4 twos in my bin 1. 2 can be replaced by 3. Okay, so there are now 3 twos and 1 3. Now the empty space in bin 1 is 1. Okay, then we remove another 2. So how many twos are there? 2 twos and 1 3. There is no unfilled item which can be packed. No, you can pack, right? And there is an improvement in arrangement. Okay. Hence, we remove another 2 and we find that packing 5, the bin 1 is filled fully. Okay. So what the algorithm seems to be that initially you pick the smallest elements, okay, and whenever there is space for a larger element, no, when there is no space for a larger element, then you pick the larger element and drop some smaller element. Now again, if there is no space, then we can remove another 2. Okay? So you removed the smallest element so far because you removed another 2. We find that there is no unfilled item which can be packed into the bin 1, and there is an improvement in arrangement. Okay, but 4 is nowhere there in your algorithm. So suddenly you went to packing 5. Yeah, I haven't completely understood what exactly is happening here. So do you, when you talk about these replacements, uh, so what do you replace by? The next largest or the largest one or which element? In my algorithm, I check if there is an item that can fully fill the bill. Hmm. Okay. So you are removing some things and then you are fully filling the bill. But then you could have fully filled it with 4 as well, right? So because uh, you had 4 twos initially, then you saw that it can be replaced by 3. Okay. So we removed another 2. Okay, okay. So that is why 4 didn't come into the picture because you kept on removing these tools, and then when you are packing 5, the bin 1 is filled fully. Then we can move on to the next tool. Okay. Now I get what this algorithm is suggesting is that you start with the smallest elements, keep on putting it in your bin, and whenever the next largest thing is not fitting in, then you remove some smaller element and put the next largest thing, and then again you remove the another smallest thing and try to fit in with some larger thing. Okay, so that that bill is packed full. Okay, yeah, this really interesting approach, uh, but you will also have to prove that this will give you close to the optimal or very close to the optimal. Okay. Okay, so yeah, there is one more thing, which is we can make a decomposition function which can make combinations for given remaining space. Okay, so yeah, maybe, but unless I see the function, how can I decide that it can make combinations for the remaining given space? Okay, because notice that just giving some algorithm is not enough. we will have to argue for any general case, not just the special case. Okay, and then we will also have to show that it is close to the optimum. Okay, for any general case. So there is plenty of work to be done here. Okay, so I'll present what algorithms are generally used for this purpose, and then how do you compare it with the optimum? Okay? Because that is also an important skill. Okay. So what the first among these is the first fit algorithm, which is place the items in the order in which they arrive and place the next item into the lowest numbered bin in which it fits. Okay. So we place the next item into the lowest numbered bin, and if it does not fit into any open bin, then we start a new bin. Okay. So it's a straightforward approach is that I don't need to sort or do anything here. Okay. Just take these items in the order in which they are appearing. Uh, so I'll start with the first item. I'll put it in the first bin. Okay. Next item is not fitting in this bin. So I'll put it in another bin. Okay, 0.8. Now 0.5 is, I will look at the lowest numbered bin. Either I could have started another bin with 0.5 in it. Bin 2, there is no option of fitting it. 0.5 can also fit in bin 1. So I'll pick the lowest numbered bin. Okay. And then I put it in bin 1, the lowest numbered bin. Then 0.1 again fits in bin 1. So I put it in other. So now bin 1 is full. Now I don't have to look at it. Then 0.7. Okay. So 7 can't go into bin 2. So it has to go in bin 3. Okay. 6 again can't go in bin 1, bin 2, or bin 3. So it has to go into bin 4. 1 has many options. It could go in this. No. So yeah, it could go in this first, second bin, right? To go in bin 3, bin 4, but I'll put it in the lowest numbered bin. Okay. And then again, 4 can't go in bin 1, bin 2, or bin 3, so I'll put it in bin 4. Okay. 2 has option of going into bin 3, so I'll put it in bin 3. And finally, the remaining 2 can't go in 1, 2, 3, or 4, so it will go in bin 5. Okay. So whenever a new object is coming, I will choose the lowest numbered bin in which it can fit and then just put it into it. Okay. And now I want to claim that this is a true approximation for the bin packing problem. Okay. So how will this strategy compare with the optimum packing? Right? That's what we want to see. So first thing to notice is that it packs all the items, right? Because it's just finding the lowest numbered bin and filling. If it fits into that, it will pack it into that bin. Right? So all the items. That is not an issue. The algorithm is also polynomial time because every time I have to pick some lowest numbered bin, and that can always be done in polynomial time and just fit it. So the algorithm is polynomial time. And the third thing is approximation factor, right? This is the harder thing, that suppose we don't know how to compute the optimum solution and still we want to compare it with the optimum solution. Okay. So you not necessary that you have to look at these algorithms and try. You can compare your proposed algorithm and try to find some approximation factor for that algorithm. Okay. In most cases, you will only get a 2 approximation. It is difficult to prove a better than 2 approximation. Let's say I have some 1.6 or 1.7. So slightly more details and are required. Okay. So let's C star with the optimum number of bins. We will say that our first fit algorithm will use C bins. Okay. Now the first observation here is let's say first fit algorithm. Is it possible that any 2 bins are less than half full? Right. So can it have that 2 bins have less than 5 capacity? So one can notice that it will never happen, that 2 bins have less than 5 capacity, right? Yeah, because if that was the case, then you would have just put it in the lowest numbered bin among these bins. And then one of the bin's contents could be put in another bin. Okay? So this is never possible, that 2 bins are less than half full. Okay? So at least C minus 1 bins are more than half full. Okay, because in this arrangement, we had the C bins. Okay, so at least C minus 1 bins are more than half full, because you cannot have 2 bins which are less than half. Okay, so at least how many bins are possible, which is summation of these AIs, right? Because what we saw was that we can sum up all the values, and whatever that sum is, that many bins you definitely require, right? If the sum is some 2.4 or 2.5, then definitely you will require 3 bins. Okay, so C star, which is the optimal solution, it is greater than equal to the sum from I equal to 1 to n up to AI. Okay, and now we want to compare our C with C star. Okay, so what we know is that at least C minus 1 bins are more than half full. Right, in whatever arrangement we are proposing, is that at least C minus 1 bins, they are more than half full. Okay, so C minus 1 by 2 is definitely less than the summation I equal to 1 to n AI. Okay, because in whatever arrangement we are proposing, C minus 1 bins are less than half full, and it can pack all these items. So C minus 1 by 2 is definitely less than the sum of all the items, right? Summation AI. Okay. Then we can write this as C minus 1 is less than twice the summation of AIs, and which is less than equal to twice C star. Okay, because we assume that C star is at least the sum of all these values, AIs, right, which is the optimum number of bits. Okay, there is a question or no? Yeah. Okay, so then we get that C minus 1 is less than twice the number of bins, and therefore C is at most twice C star, as all of them are integers. Right, because this twice C star can at most go up to, because we assume that C minus 1 is even, and therefore you can always write that C is also at most twice C star. And therefore the approximation factor is 2. Okay. So I hope this analysis is clear. If there are any questions, regarding this? Okay. So try to come up with these kind of arguments for whatever algorithm you are proposing and try to see whether you can do better than. So here the main observation was that uh, you can't have two bins which are less than half full. Okay? So all of them have to be at least half full, and based on that we derived this bound that whatever approach we are proposing, that will be less than twice the optimum solution. Okay. So this was the main observation. Can any two bins are less than half? And almost all the approximation arguments I know, they are making use of these things. Can any two bins are less than half? Based on that, we conclude. Okay. So I want to tell you two more algorithms here. One is the next fit algorithm. So in fact, this was what one of you had proposed, is that whenever there is no space, then we try to fit it in the next bit. Okay. And we just keep on doing this, right? Okay. So what is next fit algorithm? Place the next item into the current bin if it fits. Otherwise, we put it in the next bin. Okay. And there is one more algorithm which is called the best fit algorithm, which is place the next item into that bin. So this is also one of you had proposed, is that we place the next item into that bin, which leaves the least room left over after that item has been placed in that bin. Okay. And for all of these, in fact, all of these algorithms are a two approximation. Okay. So how do you see that? Let's say we want to claim about next fit. Why is it a two approximation algorithm? We'll use the same strategy as we used here. That so whenever there is no space, we put it in the next bin, right? So again, we can say that there cannot be any two bins which are less than half full, right? Because if there is already a space to fit it in the first bin, you are not going to open a new bin. Okay. So again, this observation works, and again, you can say that at least C minus 1 bins are more than half full, and at least how many bins are possible, summation AI. So the optimal solution will be at least this much. And we know that C minus 1 by 2 is less than this value, which is less than twice C star. Okay. So if you are claiming that your proposed algorithm is giving you certain things better, you have to come up with something better than this thing. Okay. There cannot be two bins which are less than half. Okay. So any questions on this thing? What our proposed algorithm is and how we are analyzing the approximation factor? Okay, if this is fine, then start with the next problem. So we have 10 more minutes. I'll introduce to you the next problem, which you can think about. So let me open the file. Okay, there is one question. See. Can you confirm for finding the approximation factor, we find the relation between solution by our algorithm and the optimum solution? Yeah, exactly. So mostly what we have done is that whatever is the solution by our algorithm, that is at most some twice or thrice or log n times the optimum solution. Okay. So we don't know the optimum solution, but we know certain facts about the optimum solution, which is it is less than or greater than something. And based on that, we conclude this relation between the solution by our algorithm and the optimum solution. Okay. So in the remaining 5 minutes, I will just introduce to you this problem, which is called a load balancing problem or scheduling jobs on identical parallel machines. Okay. So you are given a set of n jobs. Each job has some processing time, and there are m machines which can process the jobs. Okay. So let Ci be the completion time of this job. Ci, so let's say there are m many printers, and these are the documents which we want to print. Okay. Each of these documents has some processing time depending on their length, and Ci be the completion time. And the goal is to minimize the maximum completion time of any job. Okay. And this is what we call the make span. Okay, we assume that all jobs are ready at time 0, and you can schedule it on these machines and try to reduce the maximum completion time. Okay. So let's say these are the jobs, their completion times, the processing times are 5, 3, 7, 4, 6, and you can schedule this as follows, right? So let's say machine 1 gets 7 time job first, then 3, okay? Here machine 2 gets 5 and 4, and machine 3 gets 6. So what is the max span? It's the maximum time taken, which is 7 plus 3, 10. Okay, so C max will be 10 due to this job J2, right? So another arrangement could be that this 3 length job, we bring it to M3, right? In that case, C max will just become 9. So we want to minimize the maximum total time taken uh, this way, and obviously we can't hope for exact solutions. Again, it is difficult. And try to prove that this problem is NP complete by giving a reduction to some known problem. And yeah, so and also we want to give some kind of approximation algorithm for this. Okay, yeah, you can think about this, what we can do to minimize the make span. And if there are any questions regarding this problem or the approximation factor we have analyzed initially, let me know. Okay, if there is nothing, we'll stop the meeting now. See this on Monday.